Welcome to this video. In this video, we will see the addition and subtraction of floating point numbers. So first of all, we see the outlines. First, we will see the hardware implementation of floating point arithmetic for addition and subtraction. After that, we will see the floating point addition subtraction procedure. And in the last, we will see the flowchart for addition and subtraction of floating point numbers. So now let's start with the hardware implementation. So here we can see the hardware implementation part of the floating point addition and the subtraction. So here these are the hardware requirements or the register requirements for the floating point addition and subtraction. So as you can see that it is very much similar to the fixed point arithmetic. Here are some register which are given a particular name and the parallel adder. So we'll see one by one what are the registers. So first of all we are here make clear that this from here to this is one register. Similarly from here to here this is another register, and the last one is from here to here this is the last register. So this first register whole is register is called the BR, that means the capital B and the small b, and this capital A and small a is called AC register. Similarly the last one Q and the small q, the combination of these two is the QR register. So now we'll see one by one what are the different registers are available or required for addition and subtraction. First of all, in each register we'll see the registers are subdivided into two parts, as I have already mentioned. So the first part, which is in the capital letter, suppose here it is B, it is for the mantissa part, and the small b, the small or lowercase letter b, this is for the your exponent part. Similarly, here you can see that for A, capital A, this is the your mantissa part, and the small a is the exponent part. Here also the Q, capital Q is the your mantissa part and small q is the exponent part. So the AC, the register AC has mantissa sign bit as AS, that is this one. This bit is the sign bit of the mantissa, set bit of the mantissa A, and the rest of this, that is including this A and A1, this is the magnitude part. So actually this A1 and A corresponds to the total A register, okay, and AS is the your sign bit. Similarly for other two registers, this BS and QS are the sign bits, and the B and Q are the magnitude part. So in A register you can see that this A1 is individually labeled, okay. Why it is labeled? Because the result of the addition or subtraction is stored in this AC register, and this A1 should be 1 or it should be normalized to 1 so that we can get the appropriate result. Next we can see that two parallel adders are there. These parallel adders are for addition of the mantissas, and this parallel adder is for the addition of the exponent part. So as you can see that this exponent part, all exponent part don't have any distinct sign bits, okay. So lastly this E register, this not register, this is the E flip-flop. This E flip-flop is to store the overflow in the addition or the subtraction operation. So these are the register requirements for the hardware implementation of the floating point arithmetic for addition and subtraction. So we see the procedure for floating point addition and subtraction. First, we have to, before addition and subtraction, two floating point number, their exponent must be equalized. That means the exponent of the two numbers should be equal. Before addition and subtraction, we have to make sure this thing. After that, we compare the magnitude of the two exponent and make suitable alignment of the number with smaller magnitude of exponent. That means before addition or subtraction, we have to compare the two exponents whether they are equal. If they are not equal, then we have to align their two exponents by shifting the exponents or shifting the magnitude of the exponent. Next, we have to perform the addition and the subtraction, and the last, after getting the result, we have to normalize the result. That means normalization, that means the A1 register should be 1. If it is not 1, we have to make it 1 by shifting the mantissa so that the result is a normalized form. So now we'll see the algorithm, how the algorithm is divided. So mainly the algorithm for addition and subtraction are divided into 4 parts. First, we have to check for the zeros. That means if we add or subtract zeros, that means 0 plus 0 or 0 minus 0, in that case the result will be 0. So for that we have to first check the 0. Or other case may happen that suppose we have to add x and y, and x is some value, suppose x is 1 and y is 0. Y is 0. So in this case, what is the result? If we going to add, the result will be 1. So that means no operation is required. So for that we have to check first the values which are going to add or subtract, whether they are 0 or not. After that we have to align the mantissa to make the exponent equal. Okay, that means if the exponents are not equal, so we have to shift the mantissa so that the exponent should be equal. After that we'll go for addition and the subtraction, and then last normalizing the result. So these are the 4 basic parts of the algorithm for addition and subtraction of floating point number. So now we will see the flowchart for addition and the subtraction and see how it works. So suppose we want to add one number x and another number y. So if x is equal to, suppose 1 and y is equal to, suppose 0. So in this case, if we going to just add, that means what? First step is to, I have to check the value of x. So if the value of x, suppose it is 0, that means what? That means if it is yes, that means x is equal to 0. So that means the result which is in the z will be equal to the y, because y is anything, it may be 0 or not non-zero, but we don't have to check the value of y as well. So in this case directly we put the value of z equal to y. Suppose my x is not equal to 0, that means x is not 0, that is no, not 0. So in this case we'll go for check of y. If y is 0, if y is 0, that means yes, y is 0. In this case, if y is 0, that means y is 0 and x is non-zero. So result is ultimately the value of x, So now the z which stores the result, the z will be equal to x. So this is the first operation for addition. So in subtraction, what happened? We know that the subtraction is nothing but the 2's complement addition. So here, if we like to subtract two numbers, first of all, we have to take one number, suppose x as it is, and we have to take the 2's complement of y. 2's complement of y. So to take the 2's complement of y, first of all, here we have to change the sign of y. Change the sign of y, that means I have to take the 2's complement. So for subtraction, x is taken as it is and y is taken as 2's complement. And now here, after that, we'll check the x, what is if the x is 0 or not, and then we'll check for y, similar to the addition. So if both x and y are not 0, if it is x is not 0, that is no, and y is also not 0, that is no. So in this case, we'll go here in this particular location, and first we'll check the exponents equality. So as we mentioned earlier, that first of all we have to see whether the exponents are equal or not. If the exponents are not equal, suppose no, not equal, so now we have to make the exponent equal. How we can make the exponent equal? By increment the smaller exponent. Okay, so after that we'll shift the mantissa right. So we'll increment the smaller exponent part, and then after that we'll shift the mantissa right. After shifting that mantissa, we have to check whether the mantissa becomes 0 or not. Mantissa becomes 0, that means what? That means suppose it is number is 1.001. If mantissa 0, that means this part is 0. So if this part is 0, that means what? 0 point something, that means it is very small, or we can say that it is a 0 itself. So if it is 0 itself, so no further operation is required. So now if mantissa is equal to 0, that means yes, that means put the other number in the z. That means the other number is the result. So the result will be the other number and it is kept in the z and return. Return, that means what? Return is the operation is complete. Now if the mantissa is not 0, if the mantissa is not 0, that means no. So if it is no, then we will go here again and check again for the exponent. So now if I do one time or two time the mantissa exponent alignment, so now this exponent will become equal. So if it is equal, that means yes. So in this case we will go in this direction. And now we'll go for the addition. Addition signed mantissa. So we have to now add the values of the mantissa. After addition, again we have to check whether the mantissa is 0 or not. If it is 0, that means yes. If it is 0, again this kind of condition is occur, that means 0 point something 000. So 0.0000, that means it is very small, or it can be neglected, or it can be taken as 0. So in this case, if mantissa becomes 0, that means the result is now z becomes 0 and operation stopped, that means returned. So now if the mantissa is not 0, no, not 0, then we have to check the mantissa overflow. Okay, if the mantissa is not overflow, that means the overflow condition is similar to the other operations of general sign addition and the subtraction. So if mantissa is not overflow, then we'll go in this direction. If now the mantissa is overflowing, if the overflow of the mantissa, then the mantissa should be shift right, and at the same time we have to increment the exponent. So after incrementing the exponent, we have to check the exponent overflow, whether the exponent, that means exponent is the nothing but, suppose if it is a binary addition, then 2 to the power something is the exponent, suppose 0 0 0 1 0 0, it is the exponent. whether I have to check the exponent is overflowing or not. If exponent is overflow, that is yes, then report overflow. That means overflow is there, we have to, our algorithm reported the overflow and there is no result. That means there is showing error and the operation will be stopped here. So now if the exponent overflow is not there or the mantissa overflow is also not there, so in the both the cases we have to go here and do the last step. What is the last step? We have to now normalize the result. Normalizing the result, that means what we have to make the A1 register equal to 1. Okay, so for that we have to first check whether the result is normalized. If the result is normalized, that means A1 is equal to 1. A1 is equal to 1. If it is normalized, that is yes, then round the result and this is the final result. If it is already normalized. If it is not normalized, that is A1 is not equal to 1. So in this case, we have to shift the mantissa left and then decrement the exponent at the same time. Now we have to check the exponent underflow. Underflow, that means the value of the exponent is very small. So if it is very small, yes, then report underflow and there is no result, that is error in the result and operation will be terminated. Now if the exponent overflow is not there, no, then again we will go here and go for the normalization. So after that we'll get the final result. So in this way we can see that how the addition and the subtraction of floating point numbers can be done with the help of this flowchart. Okay, so in other video we'll see the one example and see how we can perform the addition and subtraction for floating point numbers. So thank you for watching the video.